Okay, so that's how you find Young's modulus. Go to the linear region, find the slope, use sigma divided by epsilon, you find Young's modulus. Young's modulus, it's a property, a mechanical property of a given material. And the reason I said it's come from Hooke's law. Do you guys remember Hooke's law? What is Hooke's law? Think about spring. What's the relationship between forces and how the displacement of spring and the spring constant? Forces F equals what? Negative K delta X, right? And same deal here. Epsilon stress, it's kind of like a force here, equals epsilon, which is a string, times Young's modulus. So I want to compare this with the spring. This is kind of like force. We mentioned last time, stress, it's to describe intensity of force, right? And strain here, it's the intensity for deformation, change of length. It's kind of our delta X. And E here, it's a property of material. So it's the K constant. Okay.
We'll be here right after your class, and you should be squared away for next time.
Sounds good. Thank you. No problem.
Have a good one.
Thanks. All right. So this is Hooke's law. And keep that in mind, you can only find Young's modulus from the linear region. All right. Linear region on the diagram. Let's do a quick practice. Okay. All right, never mind. Would that be easier if I just use a whiteboard in front? Or if you guys prefer just watch at the TVs? If you're just okay with watching at TV on the TVs, raise your hand. Okay. If you want me to just do everything on the whiteboard, raise your hand. Okay, cool. Okay, now let's do a practice. If we have a stress strain diagram, looks like that. Let me give them some numbers. Kilopascal. This is a string. There's no units. We have 100, 200, 300, 400. Okay, so I just gave some random numbers on this diagram so that we can practice how to find Young's modulus. Okay, so I kind of developed this 4 steps approach to find Young's modulus in case you forgot at one point during the semester how to do that. So the first step is to find a point, any point on the in the linear region. In this case, the linear region, it's this region here. So step 2 is read what is the sigma, which is the stress of the point you just picked on in that linear region. So for example, and just pick a point. You can pick any point inside of linear region. Pick this point right here. Let's call that point A. And read what is the stress at point A. That's step 2. Read sigma of point A. And in this case, from what I have on this diagram, the stress is 200 kilopascal. Write out sigma A equals 200 kilopascal. And step 3 is to read what is the sigma value of point A. Come to the diagram. All right, it's almost 0.2. Let's see, it's about 0.19. So sigma here, A, is 0.19. And step 4 is to apply Hooke's law to find what is Young's modulus. Or you can see it's apply the definition of Young's modulus. E equals sigma A over sigma over epsilon A. Plugging numbers, which is 200 kilopascal divided by 0.19. And you can use your calculator to do, so it's 200 divided by 0.09. It's about 1052.6 kilopascal. Make sure you have units. So the units for Young's modulus, it's same as stress. Pascal, kilopascal, megapascal, gigapascal. All you can use newtons per meter square. They share the same unit. And those are the 4 steps you can use if you have a stress strain diagram to find Young's modulus. Just keep in mind, you can only find the information about Young's modulus inside of the linear region. You can put that down in your notes. Only the linear region tells you the information about Young's modulus. You cannot pick a point outside the linear region. All right. Any questions about how to find Young's modulus? Just follow these 4 steps, it'll be good. Okay. So Young's modulus can be thought as stiffness of a material. Or you can think Young's modulus, it's a material's resistance to elastic deformation. You can think about as a spring. If the spring constant is large, which means the spring is pretty hard. It's really hard to push the spring, to compress or stretch the spring. It's kind of like Young's modulus. If you have large Young's modulus for a material, and it's going to be really hard to elastic deform that material. That makes sense. If you have a smaller Young's modulus, that means the material is a little bit softer. You can use a smaller force to bend it or compress it. It can recover to its original shape. So yeah, it is also a materials resistance. Resistance to elastic deformation. If you have a large Young's modulus, that will give you a very stiff material. So how would that reflect on our stress strain diagram? If you want to draw a stress strain diagram for a, let's say this material, this curve represents material A. If you have material B, which is stiffer than material A, how would you draw the stress? How can you guess how the stress strain curve looks like just for the linear region? Would yes, you will have a steeper slope. So this is for material B. A stiffer material than A, you have a stiffer linear region. What if we have a soft material? Have a less, yeah, much softer material. Let's call it material C. And so that linear region tells you the stiffness of a material. You can just judge by the slope of that linear region. And it's nice to have a material that gives you this linear looking stress strain diagram, right? So you can find what's the slope. But keep in mind, there are materials which has non-linear elastic regions. So there's no linear region on their diagram. So when that is the case, you don't have to, this is not on your exam, just something good to know. Yes. So when you have a condition that it's not possible to find the slope, for some materials, that means this material has no linear region. And there are two methods we can use to determine Young's modulus. One is called tangent. Modulus. Another one is called second modulus. Well, we won't touch materials with no linear region in this class. So most of the materials C would have a linear region for you to determine the slope, which is Young's modulus. But for non-linear materials, you have other two methods to determine the Young's modulus. Okay. And how can we use Young's modulus? So if we don't have the stress strain diagram of a material, if I only tell you material X has Young's modulus of 200 Pascal, and now you can use this information to solve some of the engineering problems. For example, let's see, we have a material X, and the Young's modulus of that material is 200 Pascal, which is very soft, I guess. Such a small number. And now I say if we want to apply a force to this material to reach a strain. Now, let's see. If we want to apply a force or stress to this material to reach change of length of 0.1 meters and determine what stress you need to apply in order to have this delta L equals 0.1 meter. Does that make sense? So that's thing. In order to solve that, we need another information, which the original length of this a bar which is made of material X is 1 meter. So how can we do that? How do we determine the needed stress in this case? Can you have 2 minutes talk to your neighbors and maybe work on this on your notebook, and you're gonna work on this together after 2 minutes. Okay, let's look at this together. So for your homework, I will require you to, you don't have to copy the whole problem statement, but at least write what are the givens and what do you need to find, and your solution. For this problem, we want to find sigma, which is the stress, and we know there's the Hooke's law that links Young's modulus, strain and stress together. Right? So the E equals sigma divided by epsilon. And now we want to find sigma. So we can change this equation a little bit. That is sigma equals E times epsilon. Do we know E? Yes, we know E. Do we know epsilon strain? No, we can find it, but this is kind of unknown, but we can use the given condition to find it. Strain equals delta L divided by the original length. We know both delta L and original length, just 0.1 meter. That is 0.1 meter. Nope. There's no units for your string. Keep that in mind. String is unitless. So now we know string is 0.1. Now we can just plug in numbers. Sigma equals 200 Pascal times 0.1, which will give us 20 Pascal. So in this case, you need to apply 20 Pascal stress to this material to reach the deformation delta L equals 0.1 meter. Pretty straightforward, very easy math. And most of the math in this class won't be very fancy and complicated. Okay, it's all about understanding. Now, I want to ask this question differently. The same material X with the same Young's modulus, same original length 1 meter long. Now, listen to the question. What is a deformation? What is the new length of this bar made of material X if I apply a 1000 Pascal stress to this bar? So we still have the same material, E equals 200 Pascal. And now we know that the original length is 1 meter. Now we know another information, which is stress equals 1000 Pascal. Find what is the change of length under this stress. Okay, for this, I want you to spend 2 minutes talk with your neighbors. See how to solve this. Talk to each other.
All you have to do is plug in everything, solve for the length.
Okay, now I want to hear how would you solve this problem? How would you guys solve this problem?
So first you have to find or use forgetting what they're called. The epsilon is sigma over E,
Okay,
and we're given sigma and E. So epsilon was 5 in this case. And then you can use epsilon is equal to delta L over L I or L1.
okay.
You just solve for the
So did you use the Hooke's law?
Yeah.
Okay. Any other different method? How do you guys solve the problem?
we plugged in everything we knew into Hooke's law. So 200 pascals for your E, and then 1,000 pascals for your force over delta L over 1 meter. And you can just multiply everything around and solve for delta L.
What is the result for delta L?
5 meters.
5 meters. Okay. Any other opinions? I would say they're not right. It is not right to do that. You want to see?
That's the same thing I got.
Okay, is that everybody got the same answer? 4 meters? Raise your hand if you got 4 meters. 5 meters, sorry, 5 meters. Okay, if this is our exam 1, unfortunately, everybody got 0. Why is that? Okay, so, Dr. L, we're not stupid. This is a simple calculation. How come we got it wrong? Okay, I tricked you guys. All right, so let's go back to the definition of this Hooke's law and Young's modulus. What did I tell you during the time we introduced the Young's modulus? It's which region would tell us information about Young's modulus? Elastic region, the linear region. So only if you have elastic deformation, we can use Hooke's law or Young's modulus. But in this case, do we know everything is in elastic region? We don't know. I didn't tell you the stress strain diagram. I only said this sigma equals 1,000 Pascal. I never told you if that is beyond the yielding stress or below the yielding stress. So in this case, the solution to this question is unknown, not enough information. In order to solve this, either you have to ask me if that 1,000 Pascal above or below yielding stress. Or you can ask me for the stress strain diagram for this material X. If you have the stress strain diagram, you can easily locate where's the 1,000 Pascal on that diagram and to decide if that is plastic deformation or elastic deformation. Because we don't have those information, if you did this, should be sigma divided by E. If you did this for this problem, and it'd be all wrong, unfortunately. But that's something I think a lot of students make mistakes. Just the Young's modulus, it's given for most of the materials. So when they get a stress, the load they apply to the material, they just look up online, find the Young's modulus, and find what is the deformation strain caused by that stress. And turn out they didn't consider if that stress is under elastic deformation or plastic deformation. And it is very important. I want you to keep that in mind. It's a very important thing. So every time you want to use Hooke's law, check, double check if that stress is within the elastic region. Okay. Make sure you make a notes on that for that example. And it has a chance to appear on your exams. Now, under under the very nervous condition when you have taken an exam, you may forget this and it may trick you again. Okay, any questions on this example? All right. Okay, next thing. We're going to talk about it's called elastic recovery. So we have a stress strain diagram. Let me ask you a few questions. if we apply a stress at point A, right here, stress at level sigma A to a material, which region we're at? Elastic region. So what happens? Let's see if we have a bar here. So if we apply this stress A, we're going to have a deformation, right? It's going to become longer. How much longer? Can read from the diagram to find what is corresponding strain for that load. And we know we're going to stretch this bar. What happens if we release the stress A? Yeah, turns back to original length. Good. So it goes back to 0 if we release sigma A. Okay. Now, what if we have another load? Let's call it sigma B. What is the deformation at this point when we apply sigma B to this bar? Yep, I heard plastic. Now we will have plastic deformation. How much deformation we're going to have? That's just reading from the diagram. Find what is the corresponding strain, right? You can use the equations to find out the change of length if you want to. But that's epsilon B, which tells us how much deformation occurs under this load sigma B, which is plastic deformation. My question for you is, what happens if I release sigma B? It's staying there? So it doesn't move at all? Okay, now it's plastic deformation. If I release sigma B, any other answers? Can you guess what happens? See that again?
It would release back to the yielding stress.
It will release back to the yielding stress. It's pretty close. So it's kind of like a spring. You guys all played with spring when you were a kid? You stretch it, you release it, goes back, you lost the definition. But sometimes you broke it. What happens? You stretch too much and you release it. What happens? It goes back a little bit, but it can't go back to its original shape and size anymore, right? So it's a kind of combination of both elastic deformation and plastic deformation. Same deal happens here. At this point, if I release sigma B, it can go back to, let me draw. If this is the original length, if I release this stress, it's a different color, it will go back a little bit. So we're gonna have a remained deformation right there. Let's call it what? LP. It is plastic deformation caused by that stress, sigma B. And that region, this length right there, let's call it LE. That's the elastic deformation. So everybody's with me? So if you apply a load is larger than the yielding stress, you would cause both elastic deformation and plastic deformation. When you release that load, only the elastic deformation can recover, goes back, but the plastic deformation remains in the material. Does that make sense? Okay, then we're gonna talk about how to use that diagram to find how much length is caused by that plastic deformation. So when you release this sigma B, there's a technique you can use to determine what deformation remains in the material. It's you find that point, find the point that you apply the stress level. Let's call this point A. And start from point A, draw a line, draw a straight line, and make that line has the same slope as the Young's modulus. So which means draw a parallel line to that linear region and pass through point A. I think everybody can do that. Draw a parallel line. And the line, the parallel line should have an intersection with your x-axis. Here's our intersection. Let's call that point B. I want to read off the value at point B. Oops. Let's don't call it B since we already used letter B. Let's use letter C instead. Let's call that point C. And the corresponding sigma is sigma C. Right there. So start from 0 to C. That's what the plastic deformation caused by this load. This is remained. Oops. Plastic deformation. Could someone tell me what is the elastic deformation caused by that? Pure elastic deformation caused by the sigma B. On the diagram. It's actually here. Between point C and let's call this point B. This is the recovered elastic deformation. Does this make sense to you guys? So if you have any load that is passing is larger than your yielding stress, for example, for the sigma B, and when you rate what's the strain, which is start from 0 all the way to point B, that strain here contains partially elastic deformation and partially plastic deformation. And it is important to know the steps how to find out the recovery. Once you release the load, how much length, change of length is remain in the material. Next Wednesday, we're gonna do an example on this. I'm gonna show you step-by-step process how to do this type of problem. But that's all for today. And if you have any questions, I have office hour today from 1 to 2 p.m. Feel free to join me on Zoom. And remember, get textbook, you have homework due this Friday.